Proposition 10. If a straight line is cut in half and any straight line added to it straight on, then the sum of the square on the whole straight line with the straight line having been added and the square on the straight line having been added is double the sum of the square on half the straight line and the square described on the sum of half the straight line and straight line having been added, as on one complete straight line. For let any straight line AB have been cut in half at point C, and let any straight line BD have been added to it straight on. I say that the sum of the squares on AD and DB is double the sum of the squares on AC and CD. For let CE have been drawn from point C at right angles to AB from proposition 1.11, and let it be made equal to each of AC and CB, proposition 1.3. And let EA and EB have been joined, and let EF have been drawn through E, parallel to AD, proposition 1.31, and let FD have been drawn through D, parallel to CE, proposition 1.31. And since some straight line EF falls across the parallel straight lines EC and FD, the internal angles CEF and EFD are thus equal to two right angles, proposition 1.29. Thus, FEB and EFD are less than two right angles, and straight lines produced from internal angles whose sum is less than two right angles meet together, postulate 5. Thus, being produced in the direction of B and D, the straight lines EB and FD will meet. Let them have been produced, and let them meet together at G, and let AG have been joined. And since AC is equal to CE, angle EAC is also equal to angle AEC, proposition 1.5. And the angle at C is a right angle. Thus, EAC and AEC are each half a right angle, proposition 1.32. So, for the same reasons, CEB and EBC are also each half a right angle. Thus, angle AEB is a right angle, and since EBC is half a right angle, DBG is thus also half a right angle, proposition 1.15. And BDG is also a right angle, for it is equal to DCE, for they are alternate angles from proposition 1.29. Thus, the remaining angle DGB is half a right angle. Thus, DGB is equal to DBG. So, side BD is also equal to side GD, proposition 1.6. Again, since EGF is half a right angle and the angle at F is a right angle, for it is equal to the opposite angle at C, proposition 1.34, the remaining angle FEG is thus half a right angle. Thus, angle EGF is equal to FEG, so the side GF is also equal to the side EF, proposition 1.6. And since EC is equal to CA, the square on EC is also equal to the square on CA. Thus, the sum of the squares on EC and CA is double the square on CA. And the square on EA is equal to the sum of the squares on EC and CA, proposition 1.47. Thus, the square on EA is double the square on AC. Again, since FG is equal to EF, the square on FG is also equal to the square on FE. Thus, the sum of the squares on GF and FE is double the square on EF, and the square on EG is equal to the sum of the squares on GF and FE, proposition 1.47. Thus, the square on EG is double the square on EF, and EF is equal to CD, proposition 1.34. Thus, the square on EG is double the square on CD. But it was also shown that the square on EA is double the square on AC. Thus, the sum of the squares on AE and EG is double the sum of the squares on AC and CD. And the square on AG is equal to the sum of the squares on AE and EG, proposition 1.47. Thus, the square on AG is double the sum of the squares on AC and CD, and the sum of the squares on AD and DG is equal to the square on AG, proposition 1.47. Thus, the sum of the squares on AD and DG is double the sum of the squares on AC and CD, and DG is equal to DB. Thus, the sum of the squares on AD and DB is double the sum of the squares on AC and CD. Thus, if a straight line is cut in half, and any straight line added to it straight on, then the sum of the square on the whole straight line with the straight line having been added and the square on the straight line having been added is double the sum of the square on half the straight line and the square described on the sum of half the straight line and straight line having been added, as on one complete straight line, which is the very thing it was required to show. Proposition 11. To cut a given straight line such that the rectangle contained by the whole straight line and one of the pieces of the straight line is equal to the square on the remaining piece. Let AB be the given straight line, so it is required to cut AB such that the rectangle contained by the whole straight line and one of the pieces of the straight line is equal to the square on the remaining piece. For let the square ABDC have been described on AB, proposition 1.46, and let AC have been cut in half at point E, proposition 1.10, and let BE have been joined, and let CA have been drawn through to point F, and let EF be made equal to BE, proposition 1.3, and let the square FH have been described on AF, proposition 1.46, and let GH have been drawn through to point K. I say that AB has been cut at H such as to make the rectangle contained by AB and BH equal to the square on AH. For since the straight line AC has been cut in half at E and FA has been added to it, the rectangle contained by CF and FA plus the square on AE is thus equal to the square on EF, proposition 2.6. And EF is equal to EB. Thus, the rectangle contained by CF and FA plus the square on AE is equal to the square on EB. But the sum of the squares on BA and AE is equal to the square on EB. For the angle at A is a right angle, proposition 1.47. Thus, the rectangle contained by CF and FA plus the square on AE is equal to the sum of the squares on BA and AE. Let the square on AE have been subtracted from both. Thus, the remaining rectangle contained by CF and FA is equal to the square on AB. And FK is the rectangle contained by CF and FA, for AF is equal to FG. And AD is the square on AB. Thus, the rectangle FK is equal to the square AD. Let rectangle AK have been subtracted from both. Thus, the remaining square FH is equal to the rectangle HD. And HD is the rectangle contained by AB and BH. For AB is equal to BD and FH is the square on HS. Thus, the rectangle contained by AB and BH is equal to the square on HA. Thus, the given straight line AB has been cut at point H, such as to make the rectangle contained by AB and BH equal to the square on HA, which is the very thing it was required to do.